In this video, we're going to talk about databases, what they are, what they do, how they work, and what you need to know about them for the CISSP certification. We will cover databases just like we cover most of the other CISSP curriculum at a very high level so you understand what they are and how they work, but no more. If you come in this from a database administrator or a similar role, you will, of course, have much more in-depth knowledge of databases, and you just need to dumb it down a bit. Answer everything from the perfect world of IST squared. So let's start out with some basics. A database is just an organized collection of data, and some of the ones we use the most are relational databases. You can see a very simplified example over here on the right. Each column is an attribute, for instance, social security number, name, or title, and each row in the database is called a tuple. For the CEO, we have that her name is Jane Doe and her social security number is 111223333. And real databases would be much larger, and they would be coupled both in parent and child relationships, and we will cover that in a minute. A database is a collection of the schemas, the tables, the queries, reports, views, and other objects we use. Having all the data is, well, nice, but we also need to make it useful. We need to make it work for us and do what we want. And we build the databases and the queries and views depending on what we're trying to do. If you think of a site like Expedia maybe, you need to go to Honolulu and you need to find a hotel on a certain day within a certain price. You enter in your dates, you enter in your price range, and then you click search. And Expedia will then query all the databases for all the hotels that are connected to the Expedia site. You don't see any of this, you just get the result. And for the administration of our databases, we would most often use, well, a database management system, DBMS, which allows us to establish that communication between the databases, other applications, the users, and do what we actually need the database to do. And some of the most popular database management systems could be MySQL, Oracle, Sybase, MongoDB, or any of these. And we often classify the database management systems with the database model that they support. And the most common type of database since the 1980s have been relational models, which today would mean an SQL language, which really just defines the logical structure of the database and how the data is stored, organized, and manipulated. And as mentioned, the most popular database is SQL, which uses the relation model. You can think of it as giant interrelated Excel spreadsheets. But there are obviously other types of databases that you need to be familiar with. That could be navigational databases. They could be databases based on hierarchies, networks, graphs, the star schema, or any of these. Most of you will probably not encounter many of these, maybe outside the hierarchy model. And then, obviously, the relational model. But for the exam, understand there are multiple different types, and as anywhere else, we choose the right one for our implementation. In most cases, though, that would be dependent on the application we're implementing, so probably the only place where we would have a choice is if we're building our own applications. And then we pick the best tool. Let's look a little more at the relational model. That's the one with the giant Excel spreadsheets. Here we organize our data into tables or relations, hence the name. And the tables or relations are made up by columns and rows. And it has to have a unique key as an identifier for each row. In the example over here on the right, that will be the social security number. Because we might have 3 Jane Does or Bob Bobsons, or we might have 5 network administrators. But the social security number is going to be unique. So the row for Jane Doe is a tuple. The row for anyone is a tuple. And all of the information ties back to the unique identifier, which is Jane Doe's social security number. Now let's say the table at the top is our primary table. That will be called the parent database table. Now for all the child database tables, we would use the social security number, and the social security number in the primary table is called the primary key. Whereas in the child table, or the one at the bottom with the pay grade and the step, it would be called the foreign key. And we have that logical separation because we don't really need all the information about Jane every time we query the database. We might have another child table that has her healthcare information, another one that has her performance reviews. So dependent on what we need, we query the parent database table and then whichever child database table we need for the information we're looking for. The key takeaways here really is the parent database table, the unique identifier is the primary key. In the child database table, it's a foreign key, and we will only have one parent database table for a certain database, but we can have hundreds or thousands of child databases. And as anywhere else, but definitely in our databases, integrity is super important. And we can run many different integrity checks on our databases. And for the exam, I would know at least these 3 types of broken integrity. First off, we have referential integrity. That's when a foreign key in a secondary table does not match the primary key in the parent table. In this case, it was the social security number. We have someone listed in the secondary table with a 544545454 social security number, but in the primary table, we don't have any employees with that social security number. In this case, it may not do a lot of damage, but it could also be an indicator that someone from the primary table was not entered incorrectly, so they may not get paid. Semantic integrity, you can see here at the top, John Doe's title is no longer CFO, he is now 120 hours. That could be his vacation or something else. Semantic integrity is the wrong type of data for a certain data attribute type. I hope 120 hours is not a title. And then we have entity integrity. Each tuple or row has to have a unique primary value. That is not null. Over here on the right, if you look at the social security numbers in the second table of the 2 first people, it is the same. Meaning in the child table, someone typed in the foreign key or the social security number of Jane Doe wrongly, and Bob Bobson is now going to get paid twice. The unique key identifier in the primary table or the primary key has to be unique. And that goes just as well for the child tables where it's a foreign key. Each key has to be unique. User-defined integrity or business integrity is a set of rules that's specified by user, and it does not belong to the entity domain of referential integrity categories. And what it really means is if a certain action occurs, then another action is triggered. That could be Jane deleting a payroll file or Jane deleting a user. If that happens, it automatically writes that record to an audit table. And we do this not just to ensure the integrity of the database, but also to ensure that users don't do things they're not supposed to. If Jane doesn't like Bob, and she can go in and change the record or delete his payroll file, Bob won't get paid. Then when payday rolls around, Bob doesn't get his money, he's going to contact the payroll office, and they can see in the audit logs that Jane deleted his record. And just like we talked about when we covered access control, having a centralized system that is well controlled and has well-defined data integrity checks will make everything better. It will improve our stability. It will improve our performance, reusability, and our maintainability. I have worked in a couple of places where we did not use this, and end users were allowed to create access databases. At some point, we did an audit and we had over 2,000 access databases, some created by the end user, some were created by DBAs. And we had every month hundreds of calls because something was broken. And most of those calls were because our employees were allowed to create whatever databases they wanted. There was no security, there was no integrity checks. None of the best practices for databases and integrity were used. The more we can integrate, the more we can automate on our database integrity checks, the better. This will take some work, this will take some tweaking, but once it is done and functional, it will cut significantly down on our workload and make our databases much more stable with much higher integrity. The databases we use today come with all these features, and it is the de facto responsibility of the database to ensure its own integrity. And de facto just means that's how we do it. While it is not a standard, it is expected that any database will do this. If you think back on the example I mentioned earlier, where there were thousands and thousands of databases, and we had hundreds of calls every month because of integrity issues with the databases. If we find ourselves in a situation like that, we can either pay another company or find a database management system that can migrate our legacy systems onto modern databases, which is what we did at my old job. But before we start the migration, we need to go through a thorough audit and figure out which of the databases we actually need. It is very common for databases to run multiple threads at the same time, and all of those threads are capable of changing the data. So if two threads at the same time try to update the same record, the database management system will try to commit the update, and if the update is unsuccessful because another thread is using the same record, the database management system will most often do a rollback or an abort and a restore from a save point. And if our database does happen to become corrupted, it has integrity issues, the database can revert to a backup copy, and since we have a log of all the transactions, we just replay them back from the journal, restoring database integrity, which is very similar to how we do backups of entire systems. We restore from the backup, and then whatever is missing since the last good backup, we can restore from the logs or from the journal. Database normalization is something we can use that will also help with our integrity, but it will also improve on many other things. And the times I've used it, we've used it when we migrated from legacy systems or legacy databases onto newer ones. Because when you migrate from older systems, a lot of times you just move a lot of, stuff over that shouldn't be there. And we do it to make the database more logically concise, organized, and consistent. And it is done by removing redundant data or data that doesn't reference anything, which improves our integrity and the availability. And database normalization has 3 forms, or rules. The first normal form, we divide the database into tables. A primary key is assigned to most or all the tables. That's the one that in the child database is the foreign key. In the example we had earlier, it was the social security number. In the second normal form, we move data that's partially dependent on the primary key to another table. Some of the databases I worked with when we did this had thousands and thousands of entries for each employee, which made it insanely slow and very hard to work with. And as with the example we had before, we don't need the payroll, the medical, the vacation, any of those in the same database table. We would have it in child tables, where the foreign key is the primary key from the primary table, the social security number. And then finally, the third normal form will remove data that's not dependent on the primary key. With the social security number, this is any data that's not related to the social security number, data that's not associated with an employee. And what we get from doing all this is we get greater overall database organization, we get a reduction in our redundant data, we get data consistency within the database, much more flexible database design, and we have a much easier time handling database security. When we did this outside of making this one database into many smaller ones, making search times, making queries much faster, we also got rid of about a third of the data that was not tied to a primary key. When one of our employees query a database, what they get presented is called a database view. That is the part of the database that they're allowed to access. Payroll might be able to access employee and payroll files. HR might be able to access everything, and the employee themselves can see parts of their data. In most cases, this would be role-based access control except for the employee themselves. And since it is role-based access control, just because you can access the data does not mean you're allowed to. You need to have a need to know. A data dictionary contains a description of the database tables or the metadata. It has all the information on the database views, the information about the authorized database administrators, user account names, privileges, audit information, the database schema, and many other things. And it's not the database itself, but it's all the logical and administrative items we need to have in place to allow people and users to access the data and the rules we have surrounding it. And the last one I mentioned there, the database schema, describes the values and attributes of the database tables, meaning names should only have letters. In the US, a social security number should only have 9 numbers, and it should only have numbers. Back to the database example we had earlier where we had some integrity issues, in the title, it should be data typed to only allow titles. We wouldn't have had the 120 hours error we had in that example.